Hello, welcome everyone. Now we are going to explain photoelectric effect. So it is observed that when a light beam, this is light beam, having frequency more than a given minimum frequency or wavelength, less than a given minimum wavelength, is incident on a metallic surface, electrons are emitted. This phenomenon is called photoelectric effect. So new incident, what observation we get is greater than new minimum. Later on we will tell it cutoff frequency, cutoff frequency, or also known as threshold frequency. Threshold frequency, this is first fact. In terms of wavelength, if lambda incident is less than lambda, this is known as cutoff cutoff wavelength. Okay, in that case electrons are ejected. In that case electrons ejected. Okay, this ejected electron is known as photoelectrons. And if these photoelectrons are accelerated in a properly maintained electric field, then the current obtained is called photoelectric current. So regarding photoelectrons photoelectrons what observation are there? First, photoelectrons are just emitted after the incident of light beam. That is, almost no time lag is observed between the incident of the light beam and emission of photoelectrons. Suppose this is metal and a light of certain frequency is hitting this metal, striking this metal. In that case electrons ejection may take place. So photoelectrons are emitted just after the incidence. Photoelectrons are just emitted after the incidence of what? Light beam. Almost no time lag. Almost, in this case, almost no time lag. That is, it is instantaneous process. Okay. So almost no time lag is observed between the incidence of the light beam and emission of photoelectrons. According to a typical study, the time lag is approx 3 into 10 raised to minus 9 second. This is very small. Okay. Second observation was that no photoelectron no photo electron is emitted if the frequency of the light of the incident light beam is less than a minimum given frequency. Characteristic of the metal involved of the metal involved no matter how high is the intensity of the incident beam of the incident beam. So what observation is there? Suppose this is a metal and suppose photon is striking over it, and frequency of photon, this is frequency of incident photon, and if this frequency is less than a fixed threshold, then in this case no emission will take place. Okay, no matter through what number of photons you are going to bombard on that metal. Okay, and the third observation was that the kinetic energy of ejected photoelectrons does not depend upon the intensity of the incident light beam. It is found to be a linear function of the frequency of the incident light beam. So these observations were tried to be explained taking help of the then accepted wave character of light, but we couldn't give a satisfactory explanation for any of the above mentioned experimental observation on the basis of the wave theory of light, because according to wave theory it takes appreciable time for energy to be transferred to the metallic surface by light wave through wave matter interaction. Correspondingly, there must be a time lag between the incidence of the light beam and ejection of the photoelectrons. Secondly, no matter what the frequency of the incident light is, if its intensity is high, electrons must be emitted from metals, because in that case energy will be transferred at higher rate. So failure of wave theory of light was that, what was the failure of wave theory of light? So failure of wave theory of light. Okay, and what is this? First, according to wave theory, when light incident on a surface, suppose this is a surface, metal surface, and light is incident over this metal surface. Energy is distributed continuously over the surface so that electron has to wait to gain sufficient energy to come out. But in experiment there is no time lag. And the second was when intensity is increased. Second was when intensity is increased, more energetic electrons should be emitted so that a stopping potential should be intensity dependent, but it is not observed. And third was, according to wave theory, if intensity is sufficient, then at each frequency electron emission is possible. It means there should not be existence of threshold frequency. So this is nothing but simply the failure of wave theory of light. So Einstein equation of photoelectric effect. Einstein equation of photoelectric effect. Albert Einstein explained the above mentioned observation, again taking help of Planck's quantum theory in 1905, for which he was awarded Nobel Prize in 1921. According to Planck's quantum theory, which I had already explained in earlier lecture, light consists of massless particle, and that massless particle is known as what? Photon, and its rest mass is what? 0. Each photon of light has a definite amount of energy that depends on the frequency or the wavelength of the light and is given by h nu or hc upon lambda. So this is energy in terms of frequency and in terms of wavelength, where h is Planck's constant. So Einstein suggested that when a light beam is incident on a metal surface, the free electrons of the metal absorb. Suppose this is metal, and if a photon is striking this metal, in that case the free electrons of the metal absorbs the entire energy of an incident photon during its collision with it. If this electron gets sufficient energy in this manner to do work against the surface adhesion of the given metallic surface and escape, then it leaves the metal and a photoelectron is found. So for an electron to escape from a metallic surface by doing work against its attractive force and get out of the force field of the metallic surface, a minimum amount of energy is required to be supplied by two electrons. This minimum energy required for an electron to escape from a metallic surface is called the work function of the given metal, which is characteristic of the material and is hence they are different for different metals. So work function of a given metal is generally represented by the symbol phi. So once again I would like to explain it. Suppose this is a metal and a photons are striking over it. So suppose electrons absorbed, this electron absorbed energy. Okay, so of course when it will get energy, it will try to get out from this metal surface. In this process this electron will have to do work, because as soon as this electron will start to go from this side to other side, a plus potential will generate here, and due to which this plus potential will try to pull it back. So during the course of ejection, electron has to do work against the force field, and in that process electron has to lost certain energy. So earlier in step first, electron acquired energy from whom? From photon. This is, and in second step electron has to do work against force field to get out from the surface. And what is happening, so suppose a photon having energy h nu, so h nu, this was photon's energy, and this was given energy to photon, this was given energy to photon, sorry, to electron. This is energy of photon which was given energy to an electron. Electron acquired this much energy and he expend certain energy in the course of coming out from the surface, so called what? Work function. This is work function. So with, and suppose there is no any collision in a ideal situation, so this will equal to rest, with rest of the energy electron go away with certain kinetic energy. So this equation is known as what? Einstein photoelectric equation. So we are doing nothing but simply we are taking audit of energy, and h nu is acquired energy by an electron and phi is lost energy by the electron in the course of going out from this metal, and k is the rest of energy with which electron comes out. Okay, so this is ideal situation in which we have not taken the possibility of any collision, but there is always certain probability of collision. So if nothing is stated, we will accept it that no collision is taking place. If it will be stated, then we will consider it. So Einstein photoelectric equation is h nu minus phi is equal to k. So this was our metal, right? So suppose phi is what? Work function. And what is work function? So the minimum energy required for an electron to escape from a metallic surface is called work function. So this is nothing but simply the minimum energy required for an electron, for an electron to escape from a what? Metallic surface is called what? The work function. Okay, and the minimum frequency, the minimum frequency of light corresponding to which the energy of a photon is equal to the work function to the work function of a given metal is called threshold frequency. Threshold frequency or cutoff frequency of that metal and corresponding wavelength is called what? Corresponding wavelength is called threshold wavelength. Okay, so what we have explained that when h nu is equal to phi, that is if k is 0, in that case nu is equal to phi upon h, and this is what? Cutoff frequency and corresponding wavelength. So we can also write this equation as hc upon lambda naught, and this is equal to phi, which implies lambda naught is equal to hc upon phi. So this lambda is known as cutoff wavelength. Okay, cutoff wavelength. So I want to tell all of you is that when kinetic energy is 0, that means when electron just come out from this metal and on the outer surface its kinetic energy is what? 0. In that case the frequency corresponding to which this happens is known as what? Cutoff frequency, and corresponding wavelength is known as what? Cutoff wavelength. So clearly when a light beam of frequency less than nu naught, so if suppose in this case, so if incident frequency is less than phi upon h, what will happen? No emission, no matter how high number of photons you are going to strike over the metal surface. So if nu incident is less than phi upon h, in that case no emission will take place, and if nu is equal to phi upon h, that means just emission. But in this case kinetic energy will be what? 0. And if nu is greater than phi upon h, emission with certain what? Kinetic energy. Okay, so suppose a photon transfers energy more than the work function of the given metal, then the photoelectrons may be ejected with a kinetic energy. and in this case Kmax is equal to h nu minus phi. So where does it came from? In fact, h nu minus phi is nothing but simply what? K. So this is the same equation. Or less than that, because a part or all of the extra energy may be lost during several collisions that the electron makes before emission. An electron on the surface only has a probability of being emitted with kinetic energy Kmax is equal to h nu minus phi, and so the kinetic energy of ejected photoelectrons may have any value range from 0 to what? H nu minus phi. On the basis of this discussion, Einstein photoelectron equation may be written as h nu minus phi is equal to kmax, and h nu is equal to phi plus half mv max whole square. Okay, one more term, and that is very important term, and that is retarding potential. Retarding potential or stopping potential. Retarding potential or stopping potential. And what is this? Suppose this is the setup and a battery is connected, a light incident over it, electrons got ejected, and of course this is at high potential and this is at low potential, so direction of electric field will be from left to right. So this is the direction of electric field from left to right, high potential to, because this is at high potential and this one is low potential, so electric field is directed from high potential to low potential. So in that case electron will feel a leftward force E into E. Okay, so suppose a light strike this positive potential plate. In that case, suppose emission take place with Kmax. This electron ejected with Kmax. So it will try to drift on this plate because it has kinetic energy. And suppose electric field is sufficient enough so that even the fastest electron will get stopped and will stop here, this point, just before the reaching of this negative potential plate. What I want to tell all of you, that suppose a potential difference V is applied between two electrodes in a vacuum tube and photoelectrons are ejected from anode. This is anode, high potential, and this is cathode. By making light of proper wavelength incident on it, then the value of applied potential difference that causes even the fastest electron to stop in traveling between anode and cathode, that is loss of entire kinetic energy, is called retarding potential. So we may write EV is equal to Kmax work energy theorem, or V is equal to Kmax upon E, and this is called retarding or stopping potential. This is the formula of stopping potential, and this is called stopping potential. Stopping slash retarding. What? Potential. In terms of retarding potential or stopping potential, Einstein photoelectric equation may be written in the form h nu minus phi is equal to E into V, as Kmax is what? E into V. Okay. So from this discussion I am going to plot certain graph and what are their meanings. Suppose we have taken here retarding potential and this is photoelectric current. On y-axis we have taken photoelectric current. So situation will be like this. And this is the point where V naught, this point correspond to V naught, and this one correspond to I, this one correspond to 2I, and this one correspond to 3I. In this case frequency is constant, nu is equal to constant, but number of photons striking per second is not constant. Okay, so here frequency is constant, and the second case is this is stopping potential, and we have taken, and this one is, sorry, on x-axis we are going to take, on x-axis we are going to take retarding potential, and on y-axis we are going to take photo electron current. So situation will be like this. This is y-axis, so situation will be like this. And what is its meaning? This correspond to nu 3, this correspond to nu 2, and this correspond to nu 1. In this case light intensity is kept constant. Light intensity is equal to constant, that is number of photons striking per second is constant, and nu 1 is greater than nu 2 is greater than what? Nu 3. So we are Einstein photoelectric equation is h nu minus phi is equal to k max is equal to E into V. So any graph we can draw. So just for understanding we are going to draw graph in between stopping potential. This is a stopping potential, right, and versus 1 upon lambda. So this is metal 1, this is metal 1, and this is metal second. So what I want to tell all of you is that the kinetic energy of emitted photoelectrons is independent of the intensity of light used, because when intensity increases, number of photoelectrons incident per second increases, and hence photoelectric current increases, but energy of a photon is independent of the intensity of light. So kinetic energy of emitted photoelectrons does not depend on the intensity of incident light beam. Secondly, the photoelectric current is independent of the frequency of the light used. When frequency of incident light is increased, the energy of one photon increases, correspondingly kinetic energy of emitted photoelectron increases, but number of incident photoelectrons per second remain unchanged, so photoelectric current does not change. One more thing I would like to tell all of you is that intensity, regarding intensity. So intensity is nothing but simply what? Energy of light passing passing through per unit area, per unit area, per unit time. So intensity is directly proportional to photon per second, directly proportional to electrons per second, directly proportional to current, and inversely proportional to d square. So I2 upon I1 is equal to d1 square upon d2 square, where I is nothing, this is I1, this is I2. I is nothing but simply current flows in the circuit, and d is the distance between between the source of light and cathode. So photoelectric effect is an instantaneous process. As soon as light is incident on the metal, photoelectrons are emitted. Second thing, I just put forth before you the work function represented the energy needed to remove the least tightly bound electrons from the surface. It depends only on the nature of the metal and independent of any other factor. Okay, so these are basic things which we have to keep in our mind, but one thing I would like to tell all of you, that it is impossible for a photon to give all its energy to the free electron. And why am I telling this? Suppose a photon having energy h nu is completely, this photon is completely, this is photon, and this is completely absorbed by a free electron. We have assumed it. Okay, so then the conservation of energy states, then the conservation of energy suggests what? H nu plus m naught c square is equal to c square p square plus m naught square c4. First, and conservation of momentum. Conservation of momentum gives what? H nu upon c is equal to p. Okay, So this is equation 2, and if we substitute the value of 2 in equation 1, we will obtain h nu plus m naught c square is equal to h square nu square plus m naught square c4. So this is from 1 and 2. So squaring both side, if you square both side, squaring both side, so if you will square both side and simplifying, we get 2h nu m naught c square, this is equal to 0, which is absurd since h nu not 0, m naught c square is not 0. So it is impossible for a photon to give all its energy to the free electron. Okay, so these were basic things which I have put forth before you. Thank you so much to all of you for showing your great patience.